session, we are going to work on the differential of trig functions, that is sec x, cosec x, and cot x. In order to do this, first of all, I need to recall the fundamental limits as h tends to 0 of sin h and cos h, which says that the limit as h tends to 0 of sin h on h is equal to 1, and the limit as h tends to 0 of cos h minus 1 on h is equal to 0. So in order to understand these principles, we are going to walk throughout examples. Let's start with example 1. Differentiate the function sec x. First of all, what is sec x? Sec x can be written as a function 1 on cos x or cos inverse of x. What does this tell us? This tells us that the first thing is, in the first form 1 on cos x, it is a quotient, it is a fraction, which tells us that we will have to use a quotient rule if we use the first form. And the second form is cos x to the power negative 1, which is a function of a function, which tells us that if we use this form, we will have to use the chain rule. So in order to understand these principles, we are going to start with the first form, 1 on cos x. And in order to do this, we will use the quotient rule. So first of all, if we all recall the quotient rule, what was the first step to do? The first step to do is identify our quotient. And what is our quotient? Or let's just rewrite the whole formula. The formula says that the d on the x of 1 on cos x is bottom t top minus top d bottom all over bottom squared. In this case, our bottom is cos x and our top is 1. So we start by differentiating the individual terms. Let's start with the first term, d on the x of 1, which is equal to 0. This is recalling our constant rule, which says that the differential of any constant gives us 0. The next term is the derivative with respect to x of cos x, which gives us negative sin x, recalling from the previous video in which we worked on the differential of sin x. The next term is cos x squared, which is cos squared x. So having all these terms, all what we need to do is resubstitute inside our initial equation, which is above. That is d on the x of 1 on cos x will now give us cos x times 0 minus 1 times sin x all over cos squared x. Simplifying this, it leaves us with sin x on cos squared x, which is sin x on cos x times 1 on cos x. And what is sin x on cos x? We all know that this is tan x. And what is 1 on cos x? We know this is sec x. So what can we then say? The differential, that is therefore the differential with respect to x of sec x, which is the differential with respect to x of 1 on cos x, is equal to tan x sec x. We box our answer. So this method is, you just need to memorize this formula, because working throughout differential of trigonometric functions, you will use this formula many and many times. So let's move on to our second example. What does this example tell us to do? Differentiate the function cosec x. Just as the previous step, just as the previous example, the first thing we need to identify is, what is cosec x? Cosec x can be written as the function 1 on sin x or sin x to the power negative 1. Just as the previous question, there are two forms in this case. Recalling, the first form needs us to use quotient rule because it's a fraction, and the second form requires us to use chain rule because it's a function of a function. So in this case, what do you think we should use? In this case, we are going to differentiate this function. We are going to use the second form, which is a function of a function. Yes, because in the first case we use the quotient rule, so in this case it's good we should differentiate. So the first thing is, what is the general expression of the differential of a function that is f of g of x? This can be written as f prime of u times g prime of x. So the first thing is we need to identify our inner function and our outer function. So what is our inner function? Our inner function is sine x. Yes. And what does our inner function is sine x? So the first thing is f prime of u, that is, whereas f of u is u to the power -1, that is replacing our inner function with u, and f prime of u, which is u to the power -1, that is the differential of u to the power -1, gives us -1 u to the power -1 minus 1, recalling our power rule, which gives us negative u to the power -1. Now we need to find g prime of x. In order to do this, we recall first of all our g of x, which is our inner function, and it is sine x. So the derivative with respect to x, I hope you guys are understanding. The derivative with respect to x of g of x is cos x. From the previous video, the part 1 of this video, which covered the differential of the basic trig functions. So g prime of x is equal to d on the x of sine x, obviously, which is equal to cos x. So if you notice, in this case, we are already having our g prime of x and our f of u, which is negative u to the -1, negative u to the -2, sorry. Replacing u with our inner function, it gives us negative sine x, all that to the -2. So in this case, we just substitute back in our initial formula, which stated that the derivative with respect to x of cosec x is equal to negative sine x to the -2 times cos x. Simplifying this gives us negative cos x on sine squared x, which gives us negative cos x on sine x times 1 on sine x. But what is cos x on sine x? Cos x on sine x is 1 on sine x on cos x, which gives us 1 on tan x. So this function simplifies to -1 on tan x times cosec x, leaving us with negative cot x, with cot being 1 on tan, times cosec x. So what can we then conclude? The derivative, that is, therefore, first of all, the derivative with respect to x of cosec x is equal to negative cot x cosec x, or better, cosec x cot x. But sorry, the negative sign there. So the derivative with respect to x of cosec x gives us negative cosec x cot x. So let's move on to our third example. In this case, we are going to differentiate, that is example 3. We'll walk through the differential of the trig function cot x. So let's write down differentiate f of x, which is cot x. So just as the previous questions, you all know the steps. The first thing is we recall the forms of cot x, or what cot x actually is. Cot x is the same thing as 1 on tan x. That is the first thing we need to understand. Cot x is 1 on tan x. And what is tan x? Tan x is sine x on cos x. That means cot x can still be written as cos x on sine x. So in this case, we still have two different forms. Both forms are fractions. That means both forms will require us to use the quotient rule. But which form should we use? Both forms will lead us to the same answers. So we will use the first form, that is 1 on tan x, because in this case it is much more simpler. So recalling first of all the quotient, we state that the derivative with respect to x of a function like 1 on tan x is equal to bottom tan x, d top, which is d on the x of 1, minus top, which is 1, d bottom, which is d on the x of tan x, all over bottom squared, which is tan x squared. The first thing we then do is differentiate the individual terms. We start with our first term, d on the x of 1, which gives us 0 from our constant rule. The next term is d on the x of tan x, which gives us sec squared x, recalling the derivative of tan x from the previous video, the part 1 of this series. Now move on to our next term, tan x squared, which is tan squared x. Obviously, we don't need to do that. All what we then need to do is substitute each and every one of these terms back into our initial equation, which leaves us with d on the x of 1 on tan x equal to tan x times 0 minus 1 times sec squared x all over tan squared x. Simplifying this, we have negative sec squared x on tan squared x. This can then be simplified further by writing, we all know that sec x is 1 on cos x, so sec squared x is negative 1 on cos squared x, that's negative sec squared x, and 1 on tan x is cos x on sin x, so 1 on tan squared x is cos squared x on sin squared x. So writing explicitly, we have this, which can then be simplified to negative 1 cos squared x cancels cos squared x, leaving us with sin squared x. So we can then conclude that, but yes, sorry, before that, we notice that negative 1 on sin squared can be written as the form 1 on sin x, all that squared, which then simplifies to cosec x, because 1 on sin x is cosec x, it simplifies to negative cosec squared x. So therefore, the derivative of the function cot x equals negative cosec squared x. We box our answers. Always we box it. So in this video, that's just it. The first thing is we are going to recall each and every differential of the basic trig functions. From the formulas, we know that the differential of sine x is equal to cos x, differential of cos x is negative sine x, differential of tan x is sec squared x. All that was done in the previous videos, and in this video we walk through the differential of sec x, which gave us sec x tan x, differential of cosec x, which gave us negative cosec x cot x, and differential of cot x, which gave us negative cosec squared x. So I want you guys to recall these formulas. Why? Because working through our trigonometric differentiation, we'll always have to recall back these formulas, because if we're given maybe a complex trig function to differentiate, we'll not have to redifferentiate these initial identities, because these identities or these basic differentials which we have worked throughout these videos will serve as the basis in order to work throughout future questions. So the first thing is, let's try and identify some similarities in this function. The differential of sin x gives us cos x, right? The differential of tan x gives us sec squared x, and the differential of cot x gives us negative cosec squared x. The formulas or the identities are similar, so all what you need to do is master them, memorize them. So in future videos, we are going to walk throughout much more complicated differentials, where we will not just have to use these trig functions, we'll have to recall, use different trig functions in order to calculate, in order to differentiate the function in general. So for a brief recap, in these past two videos, we have walked through the differential of basic trig functions. So thank you for being with us throughout this video, and hope we see you on our next. Bye.